Problem 517. Find the maximum rate of deceleration of a car on a dry, level road assuming the coefficient of static friction between tires and pavement equals 1.0. Okay, so over here for part A, first step is to do a free body diagram. This is the ground. There are three forces acting on the car. Its weight downwards, the normal force of the ground pushing up, and if the velocity is to the right, the frictional force is opposing the velocity, and the acceleration is in the same direction as the frictional force. So let's take a coordinate system x which points to the right, and I can start the problem by stating that n equals mg. Why is that? It's true because there's no acceleration in the y direction, so it's a consequence of Newton number 2 in the y direction. Using the friction model, which is presented in Coletta, the frictional force, the frictional force is equal to, there's a mistake here, it should be frictional force, F sub F is equal to mu k times n. N is equal to mg, so that's equal to mu k times mg, and for the first part of the problem mu k is assumed to be equal to 1, so the frictional force is equal to mg. Then I can use write down Newton number 2 for the x direction, which would equate to minus m times a sub x is equal to minus m times g. Now understand both of these minus signs. The minus sign here communicates that a sub x is anti-parallel to the positive direction, and this minus sign communicates that the frictional force is anti-parallel to the positive direction. So the conclusion is that the deceleration is g in the horizontal direction, assuming a mu sub k of 1. So now what we can do is we can use one of the four kinematic equations. It's in fact the equation that does not include time. So the final velocity, 0 meters per second squared, is equal to the initial velocity, 25 meters per second squared, plus 2 times the acceleration. To write this a little bit differently, it's plus 2 times the acceleration. Acceleration is negative, meters per second squared, times the stopping distance. And so we'll solve this equation for the stopping distance and conclude that delta x is equal to 25 meters per second squared divided by 2 times 9.8, which to 2 decimal places is 32 meters. Part C of the problem changes the mu to 0.1. Actually, this is a typo right here. This should be mu sub k, not mu sub static. The car's tires are moving relative to the road. So with that correction, mu sub k equals 0.1. We can, let me change this again. It looks like I've made another typo here. Frictional force is equal to mu k times m sub g, and so Newton number 2 now gives minus m a sub x is equal to minus mu k m sub g. The m's cancel, and instead of getting an acceleration of g, you get an acceleration of 0.1 g. The acceleration, in other words, is 1/10 of what it was before. And since the acceleration in computing delta x, the initial velocity is still the same. Since the acceleration is 1/10 of what it was before, the stopping distance is going to be 10 times. So 32 meters goes to 320 meters.